So this is our setup for the charging of capacitors practical. For discharging it might be a little different, but just to go over things, very important, the arrows point towards the negative end and that wants to be connected to the negative terminal on both the power pack and it wants to be connected as normal on the multimeter. We've chosen to go for 15,000 ohm resistors. You might want to choose something different. It's best to do a preliminary experiment just to find out. Now it's important to note that for a capacitor it's very difficult to get it to zero volts before you start the experiment. So we've got ours down to 0.1 volts and we're keeping it there and we're going to make sure that we take that off all our results going forward, just so that when we come to discharge it again before we start the next round of experiments, we won't have to wait for ages. We've also chosen to put our volts at 7, although because of the way the power pack works we've had to move it a little bit further. What we're going to be doing is we're going to be timing for 120 seconds, measuring about every 10 seconds and getting different results as we go. Now it's important that between each experiment you have to discharge your capacitor again, unless you're doing the discharge, which case you have to do it the other way around. So we've chosen to get it all the way down to 0.1 volts because getting it to 0 takes a really long time and it's not always practical. So we're just showing you, this is our setup. What we're going to do is we're going to attach this to the capacitor, turn on the power pack and time how long it takes. I'll time every 10 seconds what the voltage is. Ready?
Yeah, that's on. And let's turn them on. Okay, so 0 is
9.4. 1.75. 2.53. 1.36. 3.16. 3.70. 4.16. 4.59. 4.91. 5.20. 5.47. 5.69. 5.90.
Okay, that's it. So what we're trying to work out through this whole practical is tau, which is equal to RC, and that's the time constant, and that will vary depending on the capacitor. That's what we're trying to find out, the time constant. So this is a table that we used. We've got the times here from 0 to 120 seconds with 10-second intervals like we measured, and then you do 3 trials. We just had time for 1, but ideally you'd do at least 2. Then you've got ln of the voltage, And the convention for writing the units in the table, you do ln of the voltage in volts, and that's how you write that, so ln of V slash V, and then you've obviously got your voltage in volts and the time in seconds. Okay, so we're given this equation, that the voltage at any time is equal to the initial voltage times e to the minus t over rc. If we take natural logs of both sides, we come down to this line here. And then, using our laws of logs, we can split this multiplication into an addition of 2 logs. And then, in this term, we've got ln of e to the minus t over rc. Well, that just cancels to minus t over rc, because the ln and the e are inverse operators. And then we can compare this equation to the equation of a straight line, which is y equals mx plus c. And we can see that if we plot a graph of ln v on the y-axis and t on the x-axis, then we will get a straight line with a negative gradient which is equal to 1 over rc, and we'll have a y-intercept of ln of v naught. And then we can calculate the gradient of this line and come back over here, so we will have a value for the gradient, and that will be equal to minus 1 over rc. The value will be negative, and so the negatives on both sides will just cancel, and then we will be able to work out a value of rc which is equal to the time constant.